Uh, I was very lucky last week that I finally had the chance to watch the new James Bond movie. I don't know whether you already saw it, No Time to Die. But this is not the reason that I talk about James Bond today. The reason for that is that last year, at the beginning of the first Corona lockdown, we had a lot of time in the evening. All the events and everything that was usually in the evening was cancelled. So our family was at home and tried to find out what to do with all the additional spare time we had. And one of the projects we watched all the old Bond movies, so the 24 so far in a row. So from the 60s till the last one with all the different actors, and that inspired me for this presentation, not only James Bond. So I prepared a presentation for a conference last year for the Apex Connect in Germany about SQL performance tuning. And it's always good to have some stories or some examples. And here for this presentation, I use examples with James Bond characters, as you will see, and you will also see some titles of the James Bond movies. But I'm not mainly talking about James Bond, but more about performance tuning. By the way, I already introduced James Bond, but this guy here that you see on the slide, that's not the new James Bond. It looks a bit old. That's me. I'm Dani Schnider. I'm working for Trivatis, a consulting company in Zurich, in Switzerland. I'm mainly working in data warehousing field and performance tuning. I'm an ACE director. I'm active on Twitter. I have a blog which I usually use to write about Oracle data warehousing features and performance tuning, but to be honest, this year I had not much time to write a lot. But you find the blog posts from the last couple of years. I try to be more active in the future as soon as I have more time again. At the moment, I'm quite busy with many customer projects. Okay, let's just start with the topic, myths about SQL performance. Of course, because we are talking about James Bond, I have 7 myths, or better say 007 myths about SQL performance. And the first of these myths that is quite often heard is that performance is something you can do. You don't have to care when you are developing an application, and at the end or before the application goes to production environment, you can do some tests and then improve the performance by changing some parameters or adding some indexes or things like that. And let's see whether this myth is true. Obviously, it's not, as you can think. And the reason for that I will show with or explain with a small, no, actually not a small example, but an example of a performance tuning task. One of my first performance tuning tasks I had to do when I started to work for Trivatis. When you look at the performance tuning guide of the Oracle documentation, it doesn't matter which version you look at. It's just the introduction chapter. And Oracle says, okay, all the tuning tasks can be split into 3 separate areas. So performance planning, instance tuning, and SQL tuning. And most of the people, when we're talking about performance tuning, we think about these parts here. Instance tuning, that's more the DBA related stuff, so that you configure your database or your database server in a good way, that all the initORA parameters are set properly, that you have enough memory, that the disk layout is quite good, all this stuff. And of course, SQL tuning, that you have indexes, so you have current statistics, we can use partitioning, and so on. But what a lot of people don't think about is the first part, performance planning. That performance already starts with a good application design, with a proper data model, and all this stuff is also important. And why this is important, I can show you in this example. That was one of my first performance reviews I did more than 20 years ago. Together with a colleague of Trivadis, we were at the customer place. So this was a small company, and they developed an application. I can't remember the details, but my colleague looked at the database configuration, so more the DBA related stuff, and I was looking at the application and did a SQL trace. And with tkprof, I found out that this statement here that you see here is the slowest statement, or was the slowest statement that was running on this particular day on the database. And it was running for more than 3 minutes, as you can see here. And actually, it looks complex here, but that's just a select list. It does a select into some bind variables and reads from a table called AKS, whatever that means. Just one table, and we access one row of the table with the where condition on the row ID. So a very simple statement. Also, the execution plan looks simple, and it looks fast, because it is table access by a user row ID. So that's the fastest way to access a particular row in a table. So actually, there is nothing wrong with this statement, except that the statement was executed 200,000 times. And this was on a small development database at the customer place, so not a database with thousands of users, just a few developers were working there. So I asked them, so why is it possible that such a statement is executed so many times? Can you show me your application? Can we show you the data model? And what they showed me is an application which was originally written in COBOL, so very old-fashioned software developed on a mainframe, on an IBM mainframe, and then transferred it to an Oracle database and just replaced all the COBOL files or whatever they are called there. I'm not a mainframe type. They just replaced the files by tables, but the whole logic was still implemented in COBOL with embedded SQL. The data model was just a bunch of tables without any foreign keys, without any real relationships between the tables. And if they wanted to join two tables, they did it with cursor loops in the COBOL application. So to join two tables, they did a loop on one table, and for each row, they went to the other table, selected the row ID, and then used this row ID to access the particular row of the table. So in other words, the whole application had nothing to do with a relational database. They just used a traditional COBOL application and implemented their own system with the Oracle software. But that's not the way how you should use a relational database. And the best thing to do with this application is to throw it away and to start from scratch. But of course, that was not what I could write in the review document. So we tried to find out how can we configure the database, how can we add, for example, some additional indexes or whatever. But it didn't really solve the problem. And that was really the problem in this application. So when the application design is so bad, it is almost not possible to improve the performance. So it would be a much better approach to start from scratch. So the only thing we could do is that at least the long-running batch jobs, we recommended to replace them with PL SQL procedures that really use the Oracle features instead of doing all this manually in a COBOL application. So that was for me a good experience where I learned that performance tuning is not something you just can ignore during development of an application and think about it at the end of the project. That's something you really have to keep in mind for all the tasks, even when you plan your application, while you develop it, while you design the data model, when you select the hardware and all this stuff. Always keep in mind that performance is an important part of the application. From Index with Love, or From Russia with Love, that was also one of the first of the very old James Bond movies. And here from Index with Love, we all love indexes because we know an index is a good thing to improve the performance. On the other side, full table scans are bad. That's also a myth, but let's see whether that's really the case. We have two execution plans here, and both for the same statement. So it joins a couple of tables. So that's an example from a performance tuning workshop I give for the Wadis about once a month, or yeah, depending on the customers. At the moment, it's a bit less because of the Corona situation, but so here we have two different execution plans for a statement that joins 4 or 5 tables. If you look at these execution plans, what do you think? Which of the plans is faster, or which statement will run faster with the corresponding execution plan? Is it plan A or plan B? Of course, I cannot ask the audience here, but probably you can write it to the chat if you have an idea. Oh, I already pressed the button, so it's obvious that it is A. So these are two typical execution plans. The first one uses indexes, and indexes in combination with nested loops. And what you can see here is only the number of rows here, so the cardinality for each row is quite low. That means only a small amount of data is read through the indexes. So we have an index that reads all persons with a particular day of birth, 69 persons. Then we have addresses and so on. And at the end, we have 114 rows. And with all the joins, 1 row is returned at the end. The same statement could be executed with a full table scan, or with 4 full table scans, and index full scan, that's something similar, but we don't use the indexes for most of the tables, and we use hash joins. At the end, we have also 1 row. We have here also the 69 persons and so on, but we have to read more than 200,000 addresses because of the different execution plan, and because we cannot use, or the index is not used here, this plan is worse. So that means the myth seems to be true, that the index helps to improve the performance. And that's really the case for this statement or for these execution plans, but that's not always the case. If we look at another execution plan, here we have also an execution plan with a lot of full table scans and hash joins. And this execution plan, that's from another example here from a data warehouse environment. And that's a report that selects a lot of data. So from a beer brewery, that's just an example. It's not a real project, like most of the examples I show here. And here we have quite a lot of rows. And this is the case for these kind of statements. If we read all our beer deliveries and join it with customers and addresses and orders and so on and invoices. Then we have hundred thousands or millions of rows that we want to join, and this is not fast when we use indexes. So therefore, a full table scan is better. So this is actually a good execution plan, even if it doesn't use indexes at this place. And what I want to show with these two different kind of queries is there is no simple answer what is better, an index or a full table scan. If one or the other would be better, then Oracle would not have two different options. So the questions whether an index scan or a full table scan should be used depends on the selectivity. And the selectivity, that's the percentage of the data that is read from the driving table, so from the first table, or from all the tables that are the input for the next join. And if this selectivity is small, or if we call it a strong selectivity, if we have a small percentage of data, then index scan is a good choice. So if we have 200,000 rows, addresses, for example, and we want to read only 1 or 2 or 10 of them, then an index scan is a good choice. If we want to read all addresses or most of the addresses, then we have a weak selectivity, a high percentage of data, and then a full table scan is the better choice. Yeah, when does it switch? So at which percentage is a full table scan faster than an index scan? Yeah, there are also several myths where this percentage is. I don't tell you exact number because it depends on the database setup, on the data type of the join columns, of the size of the table, so how many columns, how many attributes it has, and so on. So there is no fixed rule, but the number is quite low. So it's, let's say, less than 10% of the data. To show this, I have a live demo here. The presentation, by the way, you can also find on my blog, at least the slides, but of course not the live demos, and that's why these live demos are for your eyes only. So if you are live in the session, you can see this index demo now. Okay, let's make it a bit bigger. So for my example, I will show you, I have just one table, employees table with a little bit more than 6,000 employees. And we have a couple of indexes here, 6 indexes on different columns. We have a primary key index, then some non-unique indexes. Most of the queries I will use the index on last name of the employees, but we also have, for example, an index on a column called license to kill, which is a flag, also from the James Bond movie, which employees have a license to kill, so it's a yes or a no, and some other indexes which we don't use here in this first demo. Okay. The first query, I'm searching for James Bond, or for all employees with last name Bond. We have James Bond here in this table, so one of the 6,000 employees is called Bond. So one of 6,000, so that's a very small percentage. And if we look at the execution plan, we can see the optimizer decides to use this index. So there is an index available on last name. And that's what I think most of us think, that this index is used. And that's also a good decision. And that's what the optimizer decides to do. If we do another query, we're looking for all employees with a last name that starts with B, so with a like B%. So like conditions could also use a normal B-tree index. But in this case, we have more than 400 employees, so 400,000 out of 6,000. So that's about 7 to 8% of the data. Let's see what the optimizer decides. The optimizer decides to do a full table scan. Even if the index is available, it is not used because the selectivity is too high, so the percentage of data is more than this small percentage of rows, and therefore a full table scan is the better choice. And if we are looking for employees that have a name starting with Q, so we have only 3 of them. And in this case, the selectivity is small, and therefore the index is used again with the index range scan. Index range scan means then more than 1 row can be returned. The same on a license to kill column. We have only 2 different values, yes and no. And it's also a rumor or a myth that a lot of people say, or a typical rule is if you have only a small number of distinct values, then it's usually not worth to create an index. If you have the same amount of data for each of the values. So let's say half of the employees have a license to kill, then this index would not be worth, but of course that's not a good idea if 3,000 people have a license to kill. As you know from James Bond movies, only the 00 secret agents have this license to kill, so only 9 people in this company here. So 9 out of 6,000, so the index is used. If we select all other employees that have no license to kill, we will have more than 6,000, 6,444. And here, again, a full table scan is used. So very simple examples, but just to show you, just because an index is available, it does not mean that the index is always used. It is used when it is useful. So the cost-based optimizer calculates the costs depending on the selectivity and then decides whether to use this index or not. The count is not enough, or the world is not enough, like the original title of the James Bond movie was. There is a myth that count 1, if you want to count the number of rows in a table, instead of a count star, you could do a count 1, or count on the constant, or a count on the primary key. And this is faster than a count star. At least that's what many people think. Let's prove whether this is the case. We have 3 different ways to count the number of employees of our employees table. We could do the obvious way, a count star from employees, or we could do a count 1 or a count of any constant from employees, or we could do a count of employee ID from the employees table. Just for yourself, think which is the fastest way to do that, or if you have an idea, you can write it to the chat. Somebody says B, somebody else says equal. Equal, it's actually the case. So all 3 options are exactly the same. And let's prove that. So we do a count star and look at the execution plan. And it's interesting to see that this also uses an index. And here the index on license to kill is used for this purpose, but not with the index range scan, but the so-called index fast full scan. The index fast full scan is something similar to a full table scan. So but instead of reading the whole table, it reads the whole index, so all index blocks. And here it is used only to read how many entries are in the index, so how many row IDs are stored in this index. But why on this index license to kill? That's a good question, because we have nothing about this attribute license to kill in our query. We just count the number of rows of the table. Let's look at the second example, the count one. It uses exactly the same execution plan again. So it does not matter which of whether you use a count star or a count one. And even the third option with a count on the primary key. So probably it should use the index on the primary key. But even here, it uses this index on the license to kill column. Why is exactly this index used for this query? The reason is that this is the smallest index on the table, because the flag has only one byte to store the yes or no, and then of course all the corresponding row IDs. But this index is the index with the smallest number of blocks, and that's what the Oracle does, or the optimizer decides to use the index on the smallest index on a column that is always used in this table. So one rule that this index fast full scan can be used for a count star or for to count the number of rows of the table is that the column must be set to not null. So there must be a not null constraint. If I remove this not null constraint, so if I modify the column and say license to kill can also be null, then it doesn't work anymore, because then null values are not stored in the index. And now if we do a count star or any of the other queries again, then the second smallest index is used. So in this case, the index on department ID, which is also a small index. If we look at the sizes of the index, so the number of leaf blocks per index, we see that license to kill is the smallest one, and department ID is the second one. If department ID would not be if there is not null constraint on this column, then the primary key would be used, and the primary key is always not null. So therefore, it's at least one of the indexes can be used. So back to our question, which is the fastest way to count the number of rows. So all answers are right, or the correct answer is they're all equal, all lead to the same execution plan. Okay, number 4. Yeah, I have to hurry a little bit. Live and let buy. If we buy more hardware, so this gives good performance. And that's also what is possible if we use the autonomous databases in the Oracle Cloud. So one of the typical features, or one of the ways, if your queries are too low on an autonomous database, you can just scale up the database. You can add more hardware or add more CPUs. And more CPUs, that also means you have more memory available, and then you can update your environment and your queries will be faster. So it runs on the Exadata, but the same rule can also be used on any other platform. But let's say one Exadata is not enough, you can add another one and another one and another one. Of course, you need a credit card with a high limit that you can pay it. Of course, it's always possible to just add more hardware, but it's not always the best way to do that. That's what we call the so-called Kiwi approach. Kiwi is the abbreviation for kill it with iron, just as a typical joke that is often used in IT. So with plenty of hardware, it's always possible to solve performance problems. But is this really a good idea? A couple of years ago, I was working for a customer to improve the performance of several long-running reports. And one of these reports was quite a complex statement with several common table expressions, so with statements with subselects here. Let's say 6 of these subselects, and at the end, all these intermediate results are joined together with a select distinct from A, B, C, and so on. So, of course, the real query was much more complicated, but just to give you an overview of the query. And this query was running for 4 hours, and after 4 hours, it stopped with this error message that you probably also know, that the timetable space was too small, so Oracle was not able to extend a segment in the timetable space. So what should we do here? We could use the Kiwi approach and add more hardware. In this case, that means add more disk space, or just to improve the to increase the timetable space, the size of the timetable space. But I tried to find out what exactly is the root cause for this performance issue. And the good thing with these common tables expressions is I can run them step by step. So in the first step, I just selected the result from the first expression A that was running in a few seconds. Then I joined it with B, still fast, with C still fast, and then at one place within the query, let's say in common table expression D, this was running for a long time. So I think after 10 minutes, I stopped it. So I knew, okay, it seems that the problem is here in this subselect here. So this subselect was still about 2 pages of SQL, but small enough that I could analyze it in detail and run just this part, or look at the execution plan for this part here in detail. And finally, after looking at it in detail, I found out that a join condition was missing. So it did a Cartesian product of 2 very big tables, joined it with all the rest of the stuff, and even this was running on an Exadata platform. Even the Exadata was not able to run this query, this whole query, with the existing timetable space and within a small amount of time. So the join condition was missing, and so we have 2 options here. We could increase the timetable space, or we could add the missing join condition. Yeah, I think you know which one would be the better way. If yes, you can type it in the chat. I think it's quite obvious. So obvious that nobody answers. Yeah, of course, it's B. Okay. The interesting thing is, after I added this join condition, so the table space was more than enough, and the whole query was running, I think, in 6 minutes instead of 4 hours, and it went through without additional hardware. So additional hardware is a good thing, but it's not always the best choice. Okay, the man with the golden hint. You know the golden hint? Probably not, but I can show it. We have a join of 3 tables: employees, departments, and addresses, and we're looking for the department and address of James Bond, of the address of Bond, the department MI6, and this query is running for 12 seconds, so quite slow. But of course, we can use the golden hint, and then the query is running much faster. Okay, wonderful. If I run it again, still fast. If I remove the hint, just to show that it is really the hint that helps, then the query is running for a long time again. So the hints are really good, and they are always help to improve the performance. You just have to add a good hint, and then everything is fine. Is this really the case? For this, we have to understand the concept of hints, how hints really work. A hint is nothing else than a comment that is added to the query, and it tells the optimizer what to do. But actually, if we add a hint and tell the optimizer, for example, to use a particular index, it's the other way around. So it tells the optimizer you are not allowed to use another index. So if we have the optimizer calculates a kind of a decision tree of all possible execution plans, and if we add a hint, so usually it chooses the cheapest execution plan here. So these are the costs of each execution plan. The cheapest one is this with 47. And if we tell the optimizer to use index 2 instead of index 1, we cut this branch here. And then we think that the optimizer should go in this direction. But it's not the case, because from the remaining execution plans, the optimizer decides to use the cheapest one, which is a completely different way. So we tried to do this one, but that didn't work. So because there is another option to use here. So take care if you use indexes, if you use hints, then it's not always guaranteed that these hints are really used. So sometimes it seems that they are ignored. So in this case, what we have to do is we have to also to include another hint, for example, to say leading to that this table is the driving table, and then we are lucky that the right execution plan is used. To show this in a real example, not just on the slide, is with another similar example to the previous one, but here we join only 2 tables, employees and departments, also to read James Bond. And as we have seen in the first example, so this index is a good thing here for James Bond. The index is really used, but it's not the best choice to do a merge join. So I know from the experience of the application and from the experience of SQL performance tuning that it is a much better choice to do a nested loop. So I add a hint, use NL on the departments table. That means a nested loop should be performed to join the departments table. And if we look at the execution plan, the hint is ignored. So we even see since 19C that this index is not used. Why that? Because the optimizer decides to start with the departments table, and therefore there is never an option to decide how the departments table should be joined, because the only table that is joined here is the employees table, and there is no hint about the employees table. So in this case, what we could do is we say, okay, then we say use nested loop for the employees table to force a nested loop. Okay, what happens here? A hash join is performed. Why that? If the optimizer would start with the departments table and do a nested loop, then the costs of this execution plan would increase a lot, because that's definitely not a good choice that we read all employees from all departments and then in a second step find out which of them is bond. And therefore the optimizer says, okay, the costs of this nested loop are higher than if I do hash join and start with the employees table. So it still doesn't help. And what we have to do, we have to tell the optimizer to start with the employees table and then join the departments table with a nested loop. So if we add only the hint for the join method, that does not help in this case. So it's always a good choice to also define which is the leading table. And now with these two hints, then we have the execution plan we want to use. So indexes are actual, I always say indexes, hints can help to improve performance, but it's not always guaranteed that they really help in all cases. So here as an overview, I don't explain it in detail, but if the demo was too fast, you can look at the slides afterwards to see what happens here with the decision tree, why a different execution plan was used. Okay, SQL. We don't have to care when we use SQL about performance because it's just declarative. So we just write what we want and not how we want. So it's the database that does the job. This works quite well in a lot of cases, but sometimes it does not work. As you see in this example, an exercise from our optimizing performance workshop. This query runs for a couple of seconds just to select 28 rows. And the reason for that is that the estimations of the optimizer are wrong compared to the actual rows. So what is really returned in each step. Yeah, I think I run out of time, so I skipped this part with the exact explanation, but just to see why are these numbers wrong. So we could look at how many different address types, countries, and so far we have, so we can calculate all these numbers. That's all correct. But the problem here is that here we have only 1% of the data, and the reason for that is this expression. And that's also something important to know when you do SQL performance tuning, or if you write your SQL statements. If you use functions or any kind of expressions in your where condition, it's quite difficult for the optimizer to calculate the selectivity of expression with the to-car, for example. And then when there is no additional information, for example, a function-based index or extended statistics or something like that, then the default selectivity is just 1%. So the optimizer thinks that 1% of all employees, of all persons are born in July 1990. And actually there are much less than these 1%. And this leads to if we rewrite the query and say instead of do a to-car and then select the month, we can do a between, and then the column that we use here is not changed by an expression, and then we have a much faster execution plan. So this is the fast execution plan. The original execution plan was completely different. It did the Cartesian product and a lot of things because this calculation was wrong. Okay, that went a bit fast, but I want to use the time for the last myth. That's the problem with this presentation. When I have 7 in the title, I also have to show all 7 examples. Statistics are forever. So the statistics are gathered automatically, and that's really a good thing since I think Oracle 10G, there is an automatic statistics job that runs every night that gather missing statistics. So we don't care about statistics anymore. And since Oracle 12c, it is even possible that if we do a create table as select, for example, or an insert into a direct path insert into an empty table, that the statistics are already gathered, so we don't have to care about it. And if you have Exadata and use Oracle 19c, there are even 2 more features that can be enabled to do real-time statistics and the statistics calculation every 15 minutes, and therefore the statistics are always up to date. So we don't care about statistics. Really? In this last demo, I show that this is not always the case. We have the so-called online statistics gathering since 12c. I'm here on a 19c database, so that should work. So if I do I copy the employees table and say create table as select, so employees 2 table, I create 2 indexes, license to kill and last name on this table. Then we see, oh yeah, that's great. So the statistics on this employees 2 table are already gathered just now, and we have 6,453 rows. So that's the exact number of employees in these tables. So statistics are up to date. So even here, the index statistics are also calculated, so everything is fine. So I expect that I have the same execution plans like in the first demo if I run some queries. If I look for license to kill, so then the index that was created should be used. But that's not the case. So a full table scan is performed. So what happened here? Has anybody an idea? If yes, you can write it to the chat. But I think I already can show you what is the reason for that. If we look at the statistics on a column level, we see for each column we have the number of distinct values, but we have no histograms. And histograms are additional statistics that have to be gathered if we have data that it is not well balanced. So if we have a very small number of yes values and very high number of no values, this information is needed by the optimizer to calculate the selectivity, and without histograms that is not possible. And per default with this online statistics gathering, histograms are not calculated. So if we gather the statistics, now the index is used, and the reason for that is that histogram is calculated here, so-called frequency histogram in this case. So we have a histogram, and therefore this problem is solved. But why is only histogram calculated here and not for the other columns? The reason for that is that the default setting of DBMS stats of the package to gather statistics looks at the history of the statements that were executed, and if needed, it uses the or it gathers a histogram, or it calculates a histogram for these columns. But we did only query with a where condition on license to kill. That's why we have only this histogram. So another query here, last name like Q%, it also does a full table scan. And if we gather the statistics again, now we index is used, and we have another histogram here on last name. And that's important to know because, of course, you don't copy the table every time, but that could also happen if you, let's say, you do a migration, or you copy your production database to a test environment, or you go to a new server, you do a data pump, export, import, then you gather the statistics with the default settings, and then you are surprised that all your queries are low. So it's important to know that you should also tell the Oracle on which columns histograms should be gathered. And the option here is to use this method opt parameter, this optional parameter. And then you can say for all skewed columns, so when you have columns with skewed data, it's worth to gather statistics. And then here in this case, we have histograms on every column. So even if everything seems to be automated, it's still a good decision to know how these statistics gathering works. Okay, I'm a bit out of time, but we still have some time to answer questions. But first, let's look which of these 7 myths I showed you are true. So performance is something you look at the end of the project. It's obviously wrong, so you should look at it all the lifetime of a project, even if you plan your application. Index is good, full table scan is bad. Yeah, there are cases where indexes are good, but also other cases where full table scans are good. It depends on the selectivity. This is also wrong, that count 1 is faster than count star. It doesn't matter, they have the same execution plan. The 4th myth, yeah, it's true that additional hardware helps to improve performance, but it's not always the best choice. Hints force the optimizer to use a specific execution plan. That's not the case. It tells the optimizer not to use other parts of the execution plan, but if you don't add enough hints, then it still can lead to cases where the hints are ignored. SQL is declarative, that's true, but you have really to take care how to write it. Otherwise, you will have performance problems, especially with function calls in their conditions. And statistics are automatically gathered, that's also true, but it's still good to know how you can gather statistics manually, or how the DBMS stats package works in detail. And then there are 2 more myths. So the hint, the golden hint makes every query faster, and that's obviously not the case. And James Bond always wins. At least one myth is true. He always saves the world, even in the newest movie, but I don't talk about the details if you have not seen the movie. Okay, that's it. I'm at the end of the presentation. Are there any questions? Yeah, in some cases, using between in the date statement will not use index. If you use greater or equal and less or equal, does this help? Actually not, because between is just a short way to write. So when you say between, so column between A and B, that's the same. So it is transferred internally to column greater or equal than A, and column less or equal than B. So it doesn't matter whether you write it in this way or you use the between. it has nothing to do whether an index is used or not. If the index is not used in your particular example, it's probably because of the selectivity. So if the number of rows between the two date fields are too high, then the index is not used. Hope this helps. Are there other questions? Yeah, there is in the Q&A part, there is a question, according to the experience, why merge is worse than nested loops. Yeah, that's we have three different join methods: nested loops, merge, and hash joins. Nested loops are good for small selectivity. If you have only a small number of rows, nested loops is the best way. And a merge statement was originally introduced for a high number of rows, but usually a hash join is faster than a merge statement. And a merge statement is only used in very rare situations, for example, for non-equi joins. So if you have a where condition that has something else than an equal sign between the two join columns, or if you do a merge, a Cartesian product, or things like that. But usually it really depends, again, on the selectivity. So as a rule of thumb, you can say for small selectivity, nested loop is the fastest way. For high selectivity, hash join, and merge is somewhere in the middle. Okay. So thank you for the presentation. Okay, I only have off-top question. What is, yeah, okay, that's a good question. What is your favorite James Bond soundtrack? That's hard to, I'm not prepared to this. There are a lot of things, but yeah, I think the soundtrack, I would say Live and Let Die. That's one of my favorites. And also the new one I also like, but I really have to compare it in detail and listen to all the music again. Okay, good. I'm still missing one question that I expected that somebody would ask. What about the golden hint? Yeah, exactly. Yeah, what that's now the question, the golden hint. At least for this question, I'm prepared. And I'll show you the golden hint example again. So without the golden hint, this statement is running for a couple of seconds. I think it was 12 seconds before. Yeah, here out 12.9, almost 13 seconds. And when we look at the execution plan, no, with the golden hint, it works much faster now. If we do an explain plan, so if we look at the execution plan for the version without the hint, then we see it does a very bad execution plan. It does a full table scan on all three tables. It does a nested loop in combination with a full table scan, which is definitely a bad choice. And it starts with the address table, the only table where we have no restrictions. So completely wrong execution plan. And the reason for that is, at the beginning of the demo, I created a SQL plan baseline. That means whenever this particular statement is executed, I tell Oracle you could you should use this particular execution plan. Yeah, I just finished. And with the golden hint, this SQL plan baseline is ignored. Also, the hint is ignored because it's a wrong hint, and therefore the nested loop, so a good execution plan, is used. Okay, the last comment is I'm out of time, so that's it for the moment. So I think then Chris can start his next session.